Hey guys, I hope you guys are all okay. This is an update video to the 433 MHz You Can't Hack This project. First of all, we're going to look at who came up with the best suggestion on how to hack the original code and what I've done to stop that from happening. We're then going to move on to project documentation. We're going to look at something called an init value, which has been added to the code. We're going to look at something called RX lockout, which has been added to the code when a hack attack is performed. We're going to talk about adding the support for 4 buttons, which has been done. We're going to talk about encryption, a few other little bits, and where the project's going next. So if we start off with documentation, and if you go to my GitHub project page, which there is a link in the description below, then we scroll down a bit and we can see that there's a link to the original video that I launched about a week ago, a little bit of rambling about some updates that's been done. I've put in there a solution methodology sort of statement just to give people an idea of what we're doing here. We're going to come back to this in a little while in more detail. There's a little bit of information about the timing, and then there's the all-important connections here. And please just forgive me for they're not exactly the best drawings there, and lines aren't so straight. But one-man band here, guys. So forgive me that, if you will. Okay, let's have a look at who came up with the best suggestion on how to hack the original code. And that award, if there was such a thing as an award, sadly there isn't. Maybe when I'm a millionaire, I'll do that. But the best suggestion came from a guy called Alan, and he was absolutely right. Within 600 iterations in the original code, you could keep sending the same numbers over and over again, and within 600 times. Although the latency would have played a part here, and it would have taken a little bit of time, but it was absolutely right. It would have actually found a code and unlocked the door, if you like. So let's have a look at what we've done to stop that, along with all the other things that we put in the code since. Let's move on. Okay, at this point, let's just have a gentle reminder of what the code does. We have something called a rolling code array, which has hundreds of numbers in it, and each time we press a TX button, it transmits a block of those numbers, which is user configurable depending on what you want. I've just got it set at 2 here, so if play these 2 first, these 2 next, and these 2 next. That's just for ease of testing. Obviously, you could increase this to 10 to gain more security, but of course, remember that you'd end up with more lag also. So let's just stick with the principle of 2. So we send these 2 numbers, then we send these 2 numbers, then we send these 2 numbers on each one. Now we call these the rolling codes. And when I refer in the next part to a rolling code loop, what I'm talking about is I'm talking about when we get to the very end of this array and we've used the last 2 numbers out, and we use the last 2 numbers. At that point, we call that the rolling code loop, and we would, on the original code, we would just come back here and start again. So let's discuss the init value and what I've done to change that. The init value works like this. So this is an example where the init value has been set to 3. And what happens is it goes through that rolling code. You can see we're transmitting blocks of 7 numbers at a time. And each of the blocks of 7 numbers is completely random. There's no algorithm. So if you know that, you can't work out this. It's no help to you. And we get to the end of the rolling codes array. And then we're going to apply the init value of 3. So we apply the init value of 3 to that array, and on the transmission 4, we now send these codes, which if you notice, this is that plus 3, that plus 3, that plus 3, that plus 3, etc. And if you notice, when we get to like a 15, then we roll over to a 3. I hope that makes sense. We keep going round the loop like this. Now, just bear in mind, as we just said, this rolling set of rolling codes is hundreds in length. So this is only applied rarely during the course of the transmissions. Now, the reason for doing that, making it so rare, is to ensure that if a hacker receives this set of codes, he's completely unaware that the init value has been applied. Whereas if we did the init value after every transmission 1, transmission 2, transmission 3, then we could it could create a vulnerability. Okay, so that's the first thing that's been done to stop that repeatability attack, but there's also something else, so let's move on to Rx lockout. Okay, so that's the first thing that's been done. So now just let's have a look at the new lockout function. And I just want to, in this section, I just want to cover off what we already had to explain how Alan got around it. And that is, we had a check repeated rolling code function. So it checked to ensure that every time we receive a code, it is a new code. It's not the same as the last one. And if it is the same as the last one, essentially the hacker would know, the system would just ignore it. So it could send, a hacker could send that code all day, every day, and it would just do nothing. But what Alan came up with, well, okay, so if I send a new code followed by the code that I've already read, hacked, that I know is a valid code because I intercepted it using SSDR or whatever method is used, then you could send a new code followed by the code is expecting. Then eventually, as it goes through the loop and keeps repeating, as it used to before we added the init value, then eventually it would find the code was being reused. So that's what we built in. So on top of that now, we've added the init value as already discussed, but we've also added something called a lockdown. Okay, so based on the settings that are user configurable here above, so here, these two lines say that the 10 is for if I receive 10 unsuccessful codes in a row, then I want to lock out for 60 seconds. Once 60 seconds are up, if it then receives another 10 unsuccessful, it would lock up for 2 minutes, and then another 10, 4 minutes, 8 minutes, etc. Goes up to about 9 hours. I think I calculated that out. I need to just make sure it stops at 9 hours, etc. But that will be in progress probably by the time this video has been launched. Those checks will be in place. So I think that stops Alan's attack. I think with those three things in there, which is the addition of the init value, keeping the check to make sure that it's a new code, and might extend that to be the last 5 codes transmitted, just to give a little bit of security improvement. And with the Rx lockout, should we receive 10 invalid codes in a row, which adds ever increasing time to that lockout. I think that probably covers that attack. Probably roll jam is the next thing that we need to discuss. But before we do that, let's look at something else that's been added. So the next thing that's been added is the addition of 4 buttons rather than just 1 button. And we can see with the LEDs here, these actually link into each of the buttons, just like the original RX would output. You can't see that very well, but the original RX is out here, and on this you've got 4 pins, and one of them would go live when a button was pressed. So this is button 1, button 2, button 3, button 4. As you see, the LED lights up just so we can see that we are actually triggering from the RX Nano, a pulse. The pulse is 210 milliseconds long, just like the original RX. And the idea of this now is it produces, with the addition of 2 nanos, if you've already got something that's working with, these are really hackable, as discussed in the first video. If you've got some sort of solution already in place, with the addition of a couple of nanos, you can actually make it more secure. The next topic is encryption, and rightly so. People detected in my original video that I launched last week that there were no encryption being used, and therefore, is it really secure? Well, to answer that, first of all, we need to look at why companies use encryption. The summary of that would be that it's used because the data is sensitive or could be used in some way to give somebody else an advantage, so we encrypt it so they can't see it. Now, I know we all know that, I'm not teaching you anything new there, but why do I not? I need to answer why I don't need to do that. And to do that, let's look at some examples of other manufacturers and why they're encrypting. So here, I'm going to just ask ChatGPT if it can help me with this puzzle. And I'm using very soft language here, puzzles, not can you decrypt this, because it will lock down with it, so I can't help you do anything illegal responses. So I'm asking it for a puzzle. Now, if I was just to transmit these numbers like this, then I wouldn't need ChatGPT to tell me what the next number is, but we can see that it works it out. So then I ask it, well, what about this one? And again, very simple. It works out that the next number is 8. Then I ask it about this one. Starts to get a little bit confused, but when I give it a little bit more information, it actually works out the correct next sequence. And as you can see, then I move on to my type scenario, and ChatGTP starts to get a little bit confused. It can't work it out. I give it a little bit more data, and it's still not working it out. It actually remarkably starts to look at pairs to see if there's any sort of variation in pairs, and the last numbers, because I'm transmitting seven numbers in a row. But it basically gets confused. And what I'm trying to get at with this is that other companies are using encryption because if they didn't encrypt the data, then you'd be able to predict what the next number was in the sequence. Whereas what we're doing here is applying a set of completely random numbers. And when I say random numbers, as long as the TX and RX understand what they are, I could literally just go along here and start changing numbers. And that would be fine, because there is no logical algorithm, formula that would predict the next set of numbers. It literally is a list of random numbers, and whether you choose to use the built-in random number generator, or you use a hex editor like this, and we open a file. We just choose any file on my laptop like this, and I could just go through it, and I could do anything here, couldn't I? I could take anything less, anything between 1 and 15 in sequence. Every time I came across one, I could pinch it, or I could convert anything that was above the value of 1 into a value divided by 15 to get a list of random numbers. So in other words, I could put anything in there, and you were encouraged to do so to make this list of numbers completely unique. The only thing I wouldn't want you to do is write your own really good formula that works out that creates a set of random numbers, because then by creating a formula you introduce yourself to reverse engineering, and it's not encrypted. So you must make up a good way of proper random numbers. Encryption, and I hope now people understand why not using encryption and why it's absolutely not necessary. In fact, it's better not to use it. Save the memory, because the more memory you've got, the more codes you can actually add. So then what's happening next? So the next thing is to increase the number of fobs you can have. Got a good idea how to do that. Testing it at the moment. It's in play. It's looking rather good. And it might add some protection into actually transmitting buttons too, which is very good. Also meaning that we can have a separate set of rolling codes for the different fob. I know there's some suggestions on YouTube where people who watch the original video might be thinking, oh, actually that'll help in that respect, and the ability maybe to press maybe button 4 and have this as sort of a reset sort of functionality, or whatever we might want to do with that, sending a different set of codes, a predetermined user definable set of codes, maybe a different length, different style, something completely different to make the RX do something different that we want it to do, something that a hacker wouldn't be privy to, because he would never see it unless you needed to perform that reset. So watch this space. Go and check out the actual GitHub. Please get involved if you want. Open to collaboration. I do want to stick with this methodology. I don't want to just copy what the manufacturers are doing, because you hack one, you've hacked them all. The idea here is the simplicity and the uniqueness of everybody's implementation can be completely different to another one, therefore making it more difficult to actually hack. I need to look at roll jam. That's the next thing on my list. I've actually got all the parts needed now. They've all arrived to build myself a good roll jam device, so I can actually utilize it on my design and see how I'm going to detect that and get around that. So guys, watch this space, like, subscribe, hit the notification button so you're kept up to date at all times. And I'll see you on the next one.